Hi guys, welcome back. It's Mrs. Webb here. I want to take a little time to chat with you guys about projectiles. So that's next on the docket. We've actually already briefly chatted about projectiles when we introduced the term of free fall, and we looked at objects that were being thrown straight up in the air or that were being dropped straight down, right? So we looked at that idea of projectiles in a one-dimensional plane. Now we're going to look at it in terms of a two-dimensional plane. So really when we talk projectiles, projectiles can be any object that is moving through the air. So we've looked at it in terms of a ball or, a rock or a pebble or, a penny is dropped or something like that, right? So really any object that's moving through the air and is being affected by gravity is going to be considered a projectile. Today what we're going to look at is we're going to look at horizontal projectiles specifically. And when we look at horizontal projectiles, the thing to note is that with a horizontal projectile, and I've got an image here for you of a horizontal projectile, that would be something like, something that rolls off a table and falls toward the ground in this general trajectory, right? So you can see that when you've got a horizontal projectile, that horizontal projectile is going to have movement in the x direction and in the y direction. And as a result, it's going to have a velocity, an overall velocity, but it's going to have an x and a y component to the velocity as well. And there's a couple of things that we kind of set up as our kind of starting point when we look at horizontal or look at any type of projectile. When we look at that projectile, we make a couple of assumptions, and we do that a lot in science. We make assumptions about the motion or about anything really. But in this case, we make assumptions about the motion of the object. And so what you'll notice here in this particular diagram is that as this object is falling toward the earth and is speeding up as it falls toward the earth, you're going to notice that its y component of that velocity at the beginning here is 0, because the object's not falling in a downward direction just yet. It's rolling off the table in this horizontal direction. So at this starting point here, the y component of the projectile is 0. But you can see that as we freeze frame the projectile at different points on its trajectory in the downward motion, you're going to see that the y component starts to grow, and it starts to get longer and longer as it starts to move toward the earth, as its displacement in the y direction grows. But if you compare that to the x direction, the component in the x direction, you'll notice that this arrow stays the same all the way through. So the velocity in the x direction, you'll see, is not changing at all when the object falls toward the earth. So as the object leaves the table here, the length or the magnitude of this vector, this x velocity vector, is the same all the way throughout. Okay, and the reason that happens is in the x direction, there's no real accelerated motion. We assume that the object is not being affected by things like air resistance and such. So there's nothing really impeding the x component of this velocity vector. But in the y direction, we know that gravity is continuously working in the downward direction. So in the y direction, the reason the y vector is being affected is because it's continually under the effects of gravity pulling it toward the earth. So there is a constant acceleration in the downward direction of 9.81 meters per second squared. But in the x direction, there's nothing impeding the motion. So this velocity vector is undergoing a uniform motion because the acceleration in the x direction is 0. So that's the big thing to note about 2D projectile motion, is that there's actually two separate things happening. The object is accelerating in the downward direction, but in the x direction, the object is traveling at a uniform rate. And so that's what I've summarized for you guys down here. In the x direction, the object is said to travel at a uniform rate, so acceleration is 0, and it's obeying uniform motion. And we make that assumption that it's unaffected by external forces like air resistance and all of that kind of stuff. But in the y direction, the object is uniformly accelerating at 9.81 meters per second, so it's undergoing uniform accelerated motion as it moves toward the ground. And we also say that it's unaffected by external forces such as air resistance. So we don't look at air resistance slowing down the object. We just assume that it's falling in that downward direction, unimpeded, and acceleration is 9.81 meters per second squared. So I already discussed this briefly in the above diagram, but what I do want to show you here is that you'll notice that this x and this y component, because these are vectors, remember that what we've always said is that the sum of the vectors always will add up to the resultant vector. So this object, when we say this object is falling, we don't say it's falling, at 0.5 meters per second in the y direction, or it's falling at 2.3 meters per second in the x direction. We never break velocities into components like that when we state that an object is moving. When an object is moving, like when our car is traveling, it's traveling at 110 kilometers per hour, period. We don't say it's traveling at 95 kilometers per hour in the x direction and 15 kilometers per hour in the y direction, right? So we never break it into x's and y's. And so the thing to note is that this object will have a velocity as it moves toward the ground, but because it's falling in this 2D direction, this velocity, this tangent here to the curve, this velocity is going to continually get longer and longer and longer. And up here, I should probably add, let me do it right now. Up here, I should probably add an arrow to show you that the velocity is equal. Oops, let's undo that. And let's try that again. So in this beginning portion here, I've added this red arrow just to show you that the velocity vector is equal to the x component because there's only motion in the one direction, in the x direction. But as soon as this object leaves the table here, it's going to start accelerating down toward the ground. And so at that point, because it's accelerating, remember our position time graphs, right? That position timeline starts to curve. So at that point, our velocity is a tangent. It's an instantaneous velocity as this object moves to the ground. And the sum of the y and the sum of the x is always going to add up to the magnitude of this tangent velocity at that instant in time. Okay. So at this point, when we start dealing with projectile problems, we have to look at it in terms of motion in the x direction and in the y direction. So when we did free fall problems, we could just look at our kinematics formulas, like displacement y is equal to velocity initial times change in time plus 1/2 gravity times change in time squared, right? We could just look at that one formula, solve for it, and be done with our problem. Here, what we need to do is we need to consider the fact that there is motion in the x and the y direction. So the problem has just a slightly bit more complexity than it did when we talked about free fall specifically. And so what I've got here is a couple of examples for you guys. In this first example, very much like the ball rolling off the table, I've got a bike. The bike launches itself off a cliff, so maybe this is like one of those stunt drivers that's going to launch themselves off the Grand Canyon or something like that, right? The bike launches itself off a cliff, or maybe it's a little jump or a drop off if you're a mountain biker. The cliff is 20 meters high, so it's a good distance. The cliff is 20 meters high, and the bike has a velocity of 2.0 meters per second in that forward direction upon takeoff. What is the range when it lands. Now range, when you see that word range, what that means is the distance in the x direction that the object is going to displace itself. So the range, I've got a diagram here for you. Here's my 20-meter cliff. The range is the distance from the point the object is in the air to the point that it touches down on ground. That's what we call range. So it's always that displacement in the x direction as the object is free falling through the air. Now, the other thing too is I have to make sure that I include my Rosetta. So I know that I'm always going to say that the direction of travel is the positive. So in this case, my object is launching itself here off to the right. So I'm saying right is positive. And because it's falling in this downward direction, and remember when we talked about free fall, it's more convenient for us to say that the downward motion is positive. So that was one of those exceptions to the rule. Generally up is positive, but here because the object is falling, we're going to say down is positive. And we know that the original velocity, they told us that it takes off, the bike has a velocity of 2.0 meters per second forward upon takeoff. Right? Now remember this diagram that I showed you up here. Because the object is traveling, this bike is traveling in a horizontal plane when it launches itself, the magnitude of its velocity is going to be equal to the magnitude of the x velocity, the x component, because the x component matches the direction of travel of the bike at the moment. So that's the one thing to note here, is that the v initial of the bike is also our v in the x direction. And then the other thing to note when you're doing these problems is that when it comes time to link the x direction and the y direction, the time that the object is moving through the air, the time is what is going to link the x direction and the y direction to each other. So the first thing we need to do is we need to find out, well, how long is that object falling? And I know from the problem and from the diagram that I've given you guys, I know that the object will fall a displacement, or it will displace itself in the y direction, a distance of 20 meters, 20.0 meters. I also know that because this object is moving in a horizontal plane here, even though its velocity is 2.0 meters per second, that velocity is in the x direction. So at that instant in time, this particular object has no y component to its velocity. So velocity initial in the y direction is 0 meters per second. The other thing I know is that as soon as this object leaves the cliff, it's going to start accelerating toward the ground at an accelerated rate of 9.81 meters per second squared. Now remember I said, because the object is falling, I said that down is positive. So that means that this is going to be a positive 9.81 meters per second squared. And I'm looking for how long is this object going to take to fall. So this is the kinematics formula that I've chosen to use. Displacement y is equal to velocity, I forgot my vector arrow up here, is equal to velocity initial times change in time plus 1/2 gravity times change in time squared. Now, this initial y velocity is 0, so I can just send this whole term here to 0, so I can kind of ignore it. And what I'm left with is 20 meters is equal to 1/2 times 9.81 meters per second squared times my time squared. I'm going to divide this whole term over to the other side, so I get 20 divided by 4.905 meters per second squared. And then to solve for time, to isolate for time, I'll take the square root. And I get 2.0192751 seconds. So at this point, I'm not going to round anything because I'm still not at my final answer. What the question was asking me originally is, what is the range? So what is the distance here in the x direction that the object is going to displace itself? Now remember, the only thing that will link this y direction to the x direction is the time, and I just figured out how long the object is falling. So now I'm going to look at the x direction of this motion. And I know that in the x direction, this object is moving at positive 20.0 meters per second. Positive because I said right was positive. I just figured out that the object is falling for 2.0192751 seconds. And what I want to figure out is my displacement in the x. Remember that in the x direction, this object is moving at a uniform rate, which means that I can use velocity x is equal to displacement x over time. Right? This is the only time I can use this formula is when the object has an acceleration of 0, when it's moving at a uniform rate. So I rearrange this to solve for d. I forgot my vector arrow up above. And I figure out that the object displaces itself 40.0 meters. And I need my direction here. 40.0 meters right. So the bike lands 40.0 meters away from the cliff. So that's a pretty typical horizontal projectile problem. Another example here, slightly different example, is we have a plane traveling at an altitude of 2,500 meters. It drops some food, so it drops a care package, and the package lands 2.26 kilometers west of the drop zone. And we want to figure out how long does the food take to hit the ground. And the second thing we want to figure out is what is the velocity of the plane. So I set up my problem and the object is moving. So here's my plane. The object is moving west. And because the object is traveling to the west and it's falling, in this instance, I'm going to say that west is positive and down is positive, just because it makes it's more convenient for calculating if we set the direction of motion as our positive. And so remember, there's a couple instances where it just makes more sense to contradict our norm of up and right is positive, and this is one of those instances. I know that the package is 2,500 meters above the ground. And I know that when it lands, that package is going to have moved itself or displaced itself 2.26 kilometers west, right? And the trajectory of that package, because the plane is traveling to the west, if the plane has a velocity of, X meters per second, that means that the package that's being dropped has that exact same velocity. And that means that the velocity direction is to the west when the package falls. So when the package falls, it's actually going to have a trajectory that's moving in this westerly direction. The common misconception is that the package will move in this direction to the east, but you have to remember that the original velocity vector on the package is pushing it forward. It's propelling it forward, right? So again, we have a scenario where we've got motion in two directions. There's motion in the x direction and the y direction. Because this package is being launched here with an initial velocity equal to the plane in the x direction, and the plane is flying, horizontally, that means that originally this package is only going to have velocity in the x direction, and that initial y velocity is 0 because it's not moving toward the Earth just yet. So I'm going to set up my two planes. I've got my y direction and my x direction. And sometimes for these problems, it's just easier to set this up right away and list all of the variables you know in the y direction and list all of the variables you know in the x direction. So that's what I've done here. Now what you'll notice is that in the x direction, you have two unknown variables. And in the y direction, you have one. This makes it easier for you to choose whether you're starting with your x or your y, because you can see right away that I don't have enough information in the x direction to solve just yet. So I have to start in my y direction. And again, the thing that links the x and the y direction to each other is the time. So in this case, I've got my displacement, which is 2,500 meters. I've said down is positive, so this is positive 2,500 meters. The velocity initial in the y is 0. Gravity is 9.81 meters per second squared, positive because I've said down is positive. And my time is the only thing I'm looking for. So again, I'm using displacement y is equal to v initial times time plus 1/2 gt squared. My v initial is going to 0. I'm plugging my numbers in, isolating for t, and I get that my time to fall for the package is 22.576182 seconds. Now in the direction of the x component, now I know this time. I know that this time is equal to 22.576182 seconds. So now I've got my two variables and I can solve for the unknown. And this one is easy, there's no rearranging. I just plug in my 22, oh yeah, I plug in my, and I didn't put my units, so let me just add that here. I plug in my displacement. Now the displacement is 2.26 kilometers. I need to move this into, well, I don't need to, but I change this into meters. So I've got 2,260 meters divided by 22.576182 seconds. And this gives me 100 meters per second positive. And I've said positive is west. So that's my velocity for the airplane at the beginning. And I know that the x component here is the velocity for the airplane at the beginning because the airplane was traveling in a horizontal plane. So the x component is equal to the velocity of the airplane itself. So that's horizontal projectiles, guys. We're going to leave it here for today, and then we'll practice together when we see each other next. Next time we'll add on to this concept. But as usual, bring your questions to class. Anything that didn't make sense, anything that you weren't sure about, let me know. And we will chat about this and practice this when we see each other. I hope you guys are doing well. Take care, and we will chat soon.